Hello everyone. In this video lecture, we are going to see how the step response parameters of the closed loop system are related or could be related to the frequency response of the open loop system. If we have a closer look at the T of j omega, which is our closed loop system indeed, if we check its body diagram as we did in the previous lecture, we could see that it approximately represents a transfer function of a type 0 system with dominant pose at about omega c, which is the crossover frequency. Because we know that for T of j omega, at low frequencies, the amplitude will be equal to 0 dB, and that's something that we had seen. Let me just show it to you again. I think we have an example over here. Yes, the one in red is the body plot for T. You can see that at low frequency it is 0, and at high frequency it goes down the amplitude. So it's kind of representing a type 0 system. Okay, so let's go back to the slide from where we were left. So we can think that the closed loop system is representing a type 0 system with dominant pose at about omega c. If there are other left half plane poles of T of S which are present at lower frequencies than omega c, so they are closer to the origin or to the imaginary axis, we assume that they are cancelled by left half plane zeros. So there are zeros nearby them, so their effect is negligible. And therefore, the closed loop system, the T of j omega, could be approximated as a type 0 system again, with dominant pose at about omega c. And now, since the approximate second order system representing T of S usually has a unit DC gain, at least for the type 1 or higher systems, we can assume that the underlying open loop system, the L of S that we have, is in the form of omega n squared over S times S plus 2 zeta omega n. And this will give us the transfer function for T of S as a second order system, omega n squared, over S squared plus 2 zeta omega n S plus omega n squared, for which we can draw the body plot for the amplitude as you can see over here. Now we are interested in the body plot of the T of j omega around the crossover frequency, and we will not just consider the asymptotic behavior for the low frequency or high frequency only. We want to have the exact values for the amplitude around the corner, the crossover frequency. So generally the body plot for the second order system that we have, T of j omega, will be similar to the one that I have over here. Now we can obtain the magnitude of T of j omega. It will be equal to omega n squared over the square root of omega n minus omega squared plus 4 zeta squared omega n squared omega squared. I guess it's quite straightforward to do. You just need to write down T of j omega, which is omega n squared over minus omega squared plus 2 zeta omega n j omega plus omega n squared. And then you add the denominator. You just take the real parts, omega n squared minus omega squared plus j times 2 zeta omega and omega. And then you can find out the amplitude as we have it over here. Then we are interested in finding the peak value and the frequency at which the peak value happens. So omega p and pv. And after some calculations, we can find them as you see here. So the peak value will happen at the frequency omega p, which is equal to omega n times the square root of 1 minus 2 zeta squared. And the peak value will be equal to 1 over 2 zeta times the square root of 1 minus zeta squared. If you are wondering how these values are obtained, you can just derive the expression that we have for the amplitude with respect to the omega and then find the maximum value. You set the derivative to 0 and then out of that you can find the omega p, and replacing it in the expression for the amplitude you can find the value. You should keep in mind that we will have this peak value only if zeta is between indeed 0 and 1 over square root of 2. If the value of zeta becomes bigger than this, we will not have the peak value. The peak will not happen. We can also evaluate the amplitude of t, the closed loop system, when omega is equal to omega n, and here we have the value. It will be equal to 1 over 2 zeta. If you replace omega with omega n, this part will vanish, so we will have omega n squared over square root of 4 zeta squared omega n squared, and this will be equal to omega n squared over 2 times zeta omega n squared, and this will give us 1 over 2 zeta. So we have it over here. We will keep this for now, and later we will refer to this at some point that we need that. So up to now, by referring to the amplitude expression for t of j omega, we can see that for a range of values of zeta, we will have some peak value at this frequency, and the peak value could be obtained as you can see here. And we have the amplitude of t evaluated at omega n, which is equal to 1 over 2 zeta. Alright. Now, considering that L of j omega c has unit magnitude indeed, and the phase phi c is equal to the phase of L of j omega at omega equal to omega c, we can write it in this form. Phase of L j omega c is indeed L j omega c itself is equal to e to the power of j omega c. We are indeed having this because we have the amplitude of L of j omega at omega equal to omega c is equal to 1 or 0 dB. Because that's the crossover frequency, yeah? We already have it. And we have some phase for our Lj of c, j omega c indeed. We can refer to it as phi c, and over here indeed it should be phi c, e to the power of j phi c. And we also remember that the phase margin is equal to pi plus this phi c, the angle of L where we have amplitude equal to 0 dB. Now, for amplitude of t of j omega, we can add omega indeed equal to omega c. We can write it in this form. It's equal to amplitude of L over 1 plus amplitude of 1 plus L. Amplitude of L is equal to 1, and at the denominator we replace L of j omega c with e to j phi c. And out of that, after doing these calculations, we can end up with 1 over 2 times sine of PM, or phase margin, over 2. And we have assumed that phase margin is bigger than 0, or our system is stable, okay? We are talking about the stable system. We can also assume that omega c, the crossover frequency, is a good approximation for omega n. If we have this approximation in mind, then we know that we have the amplitude of t of j omega n is equal to 1 over 2 zeta. And if we apply it here, so if we assume that omega c is almost equal to omega n, we can say that amplitude of t of j omega c is equal to 1 over 2 zeta. On the other hand, we have this expression over there as well. So it means that these are going to be equal to each other. If we set them to be equal to each other, then we will get zeta equal to sine of phase margin over 2. So you can see here a direct relation between the phase margin and the value of zeta. It means that if you have the value for zeta, you can directly have an estimate for the value of the phase margin. If phase margin is bigger than 75 degrees, we can use the approximation of zeta equal to phase margin over 2. Indeed, instead of saying that zeta is equal to sine of phase margin over 2, if phase margin is smaller than 75 degrees, we can replace sine of x with x itself, okay, to have an approximate value. So for values of phase margin is smaller than 75 degrees, we will use the approximation of zeta equal to phase margin over 2. If the phase margin is measured in radians, okay? If we measure phase margin in degrees, we will use zeta equal to phase margin over 100. So that's the case when we have phase margin is smaller than 75 degrees. Keep this in mind. Another point is that you should notice that in practice, the exact value of omega c for the second order approximation of the T of S, the closed loop system, can be obtained as follows. We need to have the amplitude of L at j omega c being equal to 1. Therefore, we'll have omega n squared over the denominator being equal to 1. And out of that, we can obtain the exact value for omega c, which is equal to omega n times this square root. So it's the one that we used here. Was an approximation, okay? But the exact value will be equal to what you see here. And you can see that for specific values of zeta, the approximation that we use would be valid. Now we can find the relation between omega n and omega c. You can see that omega n is equal to omega c over this square root at the denominator. And therefore, approximately omega n will be between omega c and 2 times omega c. It will not be exactly equal to omega c. And we can say that the approximation that we used in the previous slide, omega c equal to omega n, can be only used if zeta is not too large. If the value of zeta is small, then the approximation that we have here will be valid. You can see that if zeta approaches 0, so over here, if zeta becomes very small, it goes towards 0, this value will be neglected compared to 1. So out of this we will have 1, and 1 minus a small value could be approximated as 1, and therefore the whole square root could be replaced by 1, and omega c will become equal to omega n. So for small values of zeta, the approximation that we had would be valid. But for the large values of zeta, the approximation will not be true. And when we say that zeta is not too large, it means also that the phase margin is not too large, because they are directly related to each other. Yeah? We have the phase margin over 100 or phase margin over 2 giving us the value of zeta. We also see that the linear approximation of the relation between phase margin and zeta only holds if the phase margin is not too large. We already had the case that phase margin should be smaller than 75 degrees, but if you look at the graphs that we have over here, you can see that the approximation will be valid for the small values of the phase margin. So as the phase margin gets smaller and smaller, the approximation that we have for zeta will become more valid. Okay, now again, as a practical rule, we will use the approximation when the phase margin is smaller than 75 degrees. If phase margin is bigger than 75 degrees, then we will say that the closed loop system is behaving like a first order system, not like a second order system. And for that first order system, the omega c will be an estimate of the inverse of the associated time constant. You can see how the approximation that we have will work in it. If we have phase margin bigger than 75 degrees, we will use the first order approximation for T of S, and T of S will be almost equal to omega c over S plus omega c. So tau is equal to 1 over omega c. Yeah? If the phase margin is between 0 and 75 degrees, then the closed loop system will behave like a second order system, for which omega n will be approximated as omega c and zeta will be approximated as phase margin over 100 if we measure the phase margin in degrees. And therefore the transfer function for the closed loop system T of S will be equal to omega c squared over S squared plus phase margin times omega c over 50 times S plus omega c squared. So depending on the value that we have for the phase margin, we will use one of these two approximations. And now that we have an approximate transfer function for the closed loop system, we can guess the values for the step response parameters. So if we have the omega c and phase margin, which could be obtained from the body plot of the system, then we will have an estimate for the settling time and the overshoot. If phase margin is bigger than 75 degrees, we will use tau equal to 1 over omega c. We will have a first order system. There will be no overshoot. The rise time could be approximated as 2.2 times tau. Settling time for the 5% and 2% will be also calculated in this way. If the phase margin is between 0 and 75 degrees, then the second order approximation will be used, where omega n is equal to omega c and zeta is equal to phase margin over 100. Again, phase margin is being measured in degrees here. And then we can obtain the overshoot depending on the value of zeta, the rise time, which is equal to 1.8 over omega n, and the 5% and 2% settling time, referring to what we had studied before in it. On the other hand, if we have the settling time and overshoot as the input variables, then we can obtain the desired phase margin and desired crossover frequency, or omega c. We will obtain the value for zeta, directly referring to the value of MP, the overshoot, and then we will have an estimate for the phase margin, which will be equal to 100 times zeta. Then if the phase margin which is obtained here is bigger than 75 degrees, it means that we will have a first order approximation for the system, and then we can obtain the value for omega c referring to the rise time or referring to the settling time. On the other hand, if we have phase margin between 0 and 75 degrees, the second order approximation will be used, and then omega c could be obtained referring to the rise time, settling time, and the value of zeta, which we just have obtained. This will be basically used when you want to design a controller. Yeah, we will look at this one later in more details. So this way we can kind of relate the step response parameters and the frequency domain parameters, the crossover frequency and phase margin. But whatever we have obtained in the previous slides, these are all approximations, okay? The relations are approximations, and we will not get an exact and accurate value at all. However, this will give us some general indeed view on how different parameters would change their values if a parameter in the other domain would change. Here we have some qualitative relations in it. Yeah? If you take into account the relation between the rise time and the crossover frequency, we can see over here that as the crossover frequency becomes smaller, rise time will become bigger, and vice versa. So if you want to have a small rise time, you need to have a bigger crossover frequency. In the design mode, when you have designed the controller, then you can look at the obtained rise time, and if you are not happy with that and you want to decrease it, then you go back and increase the crossover frequency. We also have the relation between the overshoot and the phase margin. If the phase margin decreases, or overshoot will increase. If the phase margin increases, the overshoot will decrease. And this should also make sense, because as phase margin goes towards 0, we are going towards instability, and over there the overshoot will increase. At some point it will reach 100, and then the system will become unstable. And we also have the relation between the settling time and the phase margin and crossover frequency. So if you want to have a smaller settling time, the multiplication of the phase margin and the crossover frequency should become big. So you need to increase the phase margin times omega c in order to decrease the settling time. Alright, so I hope now you have an understanding of how the step response parameters of the closed loop system could be connected or could be related to the frequency domain parameters. We are done with this video. In the next videos, I'll provide you some examples of how these relations could be indeed evaluated and how we can figure out the step response parameters referring to the crossover frequency and the phase margin of the body response. Alright, so thank you for watching and see you in the next video.